There are three basic guidelines for analyzing algorithms. To compare algorithms, we consider worst case, we ignore constant factors, we ignore lower order terms. A function such as 5n square plus 6n plus 3, when we ignore constant factors, it will become n square plus n. And when we ignore lower order term, it will simply become n square. So the rate of growth of 5n square plus 6n plus 3 is same as rate of growth of n square. It is to be noted that if time complexity of a function is constant, then rate of growth does not depend on input size. Consider three algorithms A1, A2 and A3. Let A1 take constant time, A2 take n time and A3 take n square time for input size n. If we increase the input size to 2n, then A1 will still take constant time, and since its time complexity does not depend on input size, A2 will now take twice the time and A3 will now take 4n square, which we get by replacing n by 2n in n square. If we further increase input size, we can see that A1 will always take constant time, A2 will increase linearly, whereas A3 will increase exponentially. This also tells us that we cannot compare time taken for some specific points or some specific range, as that might paint a dubious whole picture. Let's see this by an example. Consider that there are two algorithms, A1 and A2. Let A1 have a growth rate of 10n, whereas A2 have a growth rate of n square. For input size n is equal to 1, value of A1 would be 10, whereas value of A2 would be 1. For n is equal to 2, value of A1 would be 20, whereas A2 would be 4. For n is equal to 3, A1 would be 30, whereas A2 would be 9. Similarly, up to n is equal to 9, value of A1 would be 90, but A2 would be 81. If we just consider the data points between 1 and 9, we will wrongly conclude that A1's rate of growth is more than A2, since the value of A1 is always greater than A2 in this range. At n is equal to 10, value of A1 becomes 100 and A2 also becomes 100. n is equal to 12, A1 would be 120, whereas A2 would be 144. At n is equal to 20, A1 would be 200, whereas A2 would be 400, and A1 would never catch up again with A2. This is because A1 with rate of growth of 10n is linear, whereas A2 with rate of growth of n square is exponential. We can visualize this if we draw their graphs. This is how A1's graph will go, and this is how A2's graph will go. And this point where the coincide is n is equal to 10, which is why when comparing rate of growth of algorithms, we compare how functions grow when n tends to infinity, which is asymptotic analysis of a function. We cannot just conclude by looking at a small set and say that since A1 is more than A2, hence rate of growth of A1 must be more than A2. We have to consider this till infinity. So this is why we learn asymptotic analysis of a function, which is when we study its rate of growth when input size tends to infinity. Asymptotic notations, which is how we represent rate of growth of a function in comparison to some other function. There are three notations: O, omega and theta, which can be further subclassified as big O and small o, big omega and small omega, and theta is just theta. Let there be two functions, t and f. Both of them has input size n. If tn is equal to big O of gn, then rate of growth of t is less than or equal to g, which is another way of saying that t will never take more time than g. So, rate of growth of t is less than or equal to g. If we use small o, Tn is small of Gn, this would mean that rate of growth of T is always less than G. Here they can be equal, here they can't be equal, which is another way of saying that T will take less time than G. Now the third one is if Tn is big omega of Gn. This would mean that rate of growth of T is greater than or equal to G, which is T will never take less time than G. Similarly, if Tn is equal to small omega of Gn, then rate of growth of T is always greater than rate of growth of G, which is T will take more time than G. And the last one, if Tn is equal to theta of Gn, then rate of growth of T is equal to G. T will take same time as G. Here what we are doing is we are giving upper bounds and lower bounds in terms of other function, making it free from lower order and constant terms, which is why we use asymptotic notations for asymptotic analysis. Now let's see an example. Let there are three functions f1, f2 and f3. Growth rates be 2n, 4n and n square. Time taken by them for various input points. N is equal to 1, there would be 2, 4, 1. For n is equal to 2, there would be 4, 8 and 4. For n is equal to 3, 6, 12. What we see between f1 and f2 is f1 is always half of f2. So f1 is half of f2. When a function can be written as a constant multiplication of other, then this would mean that the growth rate must be same. So f1 is theta of f2. Let's say that there are three functions f1, f2, f3. The time complexity is 2n, 4n and n square. If we plot the time taken by them at different points, we'll see that time taken by f2 is always twice of f1. When a function can be written as constant multiplication of other, then the growth rates must be same. So f1's growth rate is, we'll use theta since the growth rate is same as f2's growth rate. If there exists a constant greater than 0 such that f1 is c times f2, then growth rate of f1 is equal to f2. In f2 and f3, f2 is 4 times n and f3 is n times n. When n is greater than 4, at that point f3 will be more than f2. Beyond that point f3 will always be more than f2. Before that point f2 will be more. For every c greater than 0 such that f is greater than c dot g, then we can say that f is greater than g. For every c greater than 0 such that f is less than c dot g, then f is less than g. These are the cases of greater than and less than. For the cases of greater than equal to or less than equal to, what we can do is f less than equal to g is same as not of f greater than g, which is not of for every c greater than 0 such that f is greater than c dot g. This would become there exists c such that f is less than equal to g. For f greater than equal to g, we'll write not of f less than g, which would be not of for every c greater than 0, such that f less than c dot g, which would be there exists c such that f greater than g. We'll be using all these definitions in detail to explain what big O, big omega and theta exactly are. Big O notation, which gives tight upper bound for function. Big O notation can be defined as, we say that Fn is big O of Gn if and only if there exist constants C and N naught such that Fn is less than or equal to C dot Gn for every n greater than equal to n naught. Now this can be shown graphically as, let this side be time complexity and this side be input size. Then there are the Fn and Gn are two functions which have any behavior up to a point n naught. After n naught, Gn is always above Fn. So this n naught is the point after which behavior should not change. And we have to find a constant c such that Fn is less than equal to Cgn for n greater than equal to n naught. We have to find a pair c n naught. And if we can find a pair, many of such pair exist, we only have to find one. If we can find such one, that means that Fn is equal to big O of Gn. We'll use this definition to solve some questions. Fn is equal to 5n square, Gn is 4n square, and we have to check if Fn is equal to big O of Gn. We assume that Fn is equal to big O of Gn. Fn less than equal to C dot Gn using the formula. So Fn is 5n square, C is C, and Gn is 4n square. We can write as C is greater than or equal to 5 by 4. We can choose any C value based on which we will get an n naught value. C is greater than 5 by 4. Let C is equal to 2. For C is equal to 2, 5n square is less than equal to 2.4n square, or 5n square is less than equal to 8n square. We have to find a value of n for which this will be satisfied. We can find many values. It will be satisfied for n naught is equal to 0, n naught is equal to 1, but we need only one pair, and that pair is, C and n naught pair is 2 and 1. Since we found one of such pair exists, hence what we assumed in the starting was true, and Fn is big O of Gn. 5n square plus 6n plus 3 is big O of what? 5n square plus 6n plus 3. When we ignore constant factors, it will become n square plus n, and when we ignore lower order terms, it will become n square. So we can say that it is big O of n square. But now we have to prove it. 5n square plus 6n plus 3 is less than equal to 5n square plus 6n plus 3. Both of them are equal. But it is also less than or equal to 5n square plus 6n square plus 3n square. This one, it would be less than this one because we are using n square terms with all of the coefficients, which would be less than equal to 14n square, which is what we wrote here. What we did was, we took the highest order term, which is n square, and we made every term as the highest order term so we can add. When we added, we found 14n square. Condition for big O was Fn is less than or equal to C dot Gn. Now we can see that this 14 can be written as C. For C is equal to 14, and we can take any term, say n naught is equal to 0. Found a pair 14 and 0, hence what we assumed earlier was true. 5n square is big O of n square. And not only n square, since it is less than or equal to n square, it means that we can take here any other thing which is greater than n square. So we can also write that 5n square plus 6n plus 3. Here we have written big O of n square. It is also big O of n cube, big O of n to the power 4, big O of n square log n, anything which is bigger than n square. However, these are all true, but we'll always choose tightest upper bound, and tightest upper bound is n square. Hence the answer to this question would be n square. Fn is 5n cubed, Gn is 6n square, and we have to check whether Fn is big O of Gn. Assume that Fn is equal to big O of Gn, and using the definition, then Fn would be less than or equal to C dot Gn. So 5n cube is less than or equal to C dot 6n square for every n greater than or equal to n naught. We can cancel out n square. 5n is less than or equal to C dot 6, or n would be less than or equal to 6 by 5c for every n greater than or equal to n naught. Here n is less than a constant, not n greater than a constant. This and this are at contradiction with each other. It is saying that value of n must be less than something constant, and this is saying must be greater than something constant. This means that we cannot get a single pair of c and n naught. And since we cannot get a single pair, our assumption was false, and Fn is not equal to big O of Gn. Big omega notation gives the tightest lower bound of a given algorithm. We say Fn is equal to big omega of Gn if and only if there exists constants c and n naught such that Fn is greater than or equal to c dot Gn for every n greater than equal to n naught. Graphically, this can be shown in a graph of input size n and time complexity Tn. A certain behavior persists up to a point n naught, after which Fn is always more than Gn. Here also, as we saw in big O, we need to find one pair of constant c and n naught. If we can find such pair of constant, then what we assumed initially was true. We'll be using this definition to solve some questions. If we are doing this for small omega, then this greater than and equal to will be replaced with just greater than. Fn is 3n square, Gn is 6n cube, and we have to check if Fn is big omega of Gn. Assume that Fn is big omega of Gn, and using the definition, we find a pair C and N naught. If such pair exists, then what we assumed was true, else what we assumed was false. We have assumed that Fn is big omega of Gn, then using the definition, Fn is greater than or equal to C dot Gn. Fn is 3n square, greater than or equal to C dot Gn. Gn is 6n cube for every n greater than or equal to. We can cancel n square out. N would be less than or equal to 5 by 6 of c for every n greater than or equal to n naught, which means that n is less than a constant term as well as n is greater than a constant term, which are both in contradiction with each other. Hence, since we cannot find constant c and n naught, this means what we assumed was false, and Fn is not equal to big omega of Gn. Theta notation decides whether the upper and lower bounds of a given function are the same. We say Fn is theta of Gn if and only if there exists constant c1, c2 and n naught such that c1 dot Gn is less than or equal to Fn is less than or equal to c2 dot Gn for every n greater than or equal to n. Another way to write this, Fn is theta of Gn if and only if Fn is big O of Gn, and Fn is big omega of Gn. Since big O means less than or equal to and big omega means greater than or equal to, intersection it would mean equal to. Graphically this would be represented as the x-axis represents the input size and y-axis represent time complexity. There can be certain behavior up to a point and not, and after the point c2.gn, then fn is less than c2.gn and c1.gn is less than fn. If we are to solve a question, we can either solve for both of these or we can solve using this, and we have to find three constants c1, c2 and n0. If we can find all three constants, then fn is theta of gn. Now let's see some questions on time complexity in general. In the question given is time complexity of a function t as n square by 2 plus 3n. We ignore constant factors, it become n square plus n, and then we ignore lower order terms, it become n square. So the time complexity of tn is actually n square. Now the first option is time complexity of t is big O of n. Big O means less than or equal to n. Now n square is not less than or equal to n, hence the option number A is false. Option number B says time complexity of n is big omega of n. Big omega means greater than or equal to n. N square is greater than n, hence option number B is true. Option number C is theta of n square is same as n square, which is true. And option number D is big O of n cube, which means less than or equal to n cube. N square is less than n cube, hence option number D is also correct. Consider the following equality. Sum of I cube for I is equal to 0 to n is x, and the following choices for x. Which one is correct? Now we know that sum of cubes of number 0 cube plus 1 cube plus 2 cube up to n cube is x, which can be written as n square plus n plus 1 square into n plus 1 square by 4, which is n to the power 4. Time complexity for summation of cubes is n to the power 4. First one says it is same as n to the power 4. True. Second is same to the as n to the power 5. False. Second same as n to the power cube. False. And fourth one is big omega. Big omega means greater than or equal to n cube. N to the power 4 is more than n cube, so option number D is also correct. Which one of the following is true? First is n plus k to the power m. We have to find this time complexity and check whether it is same as theta of n to the power m. N plus k to the power m. We have to ignore constant factors, so we'll ignore k, and this will become n to the power m. And since there is theta of n to the power m, so option number A is true. Option number B says 2 to the power n plus 1, which can be written as 2 to the power n into 2. When we ignore constant factors, it becomes 2 to the power n. Here it says big O of 2 to the power n, which means less than or equal to. Since there is equal to, which one also be true. Option number C says 2 to the power 2n plus 1, which is 2 to the power 2n into 2. We ignore constant factors, it will become 2 to the power 2n. This is same as 2 to the power n square. We cannot ignore this 2. This is important. 2 to the power n is actually false, and option C would not be the correct answer.